For this week and the next 2 weeks, I'm going to introduce different applications of remote sensing. Um, as you know that when you're watching this video, the only exam of this course has been finished. Okay, so the next 3 lectures, they are not included in any exams or assignments. So why do I want to introduce them? Because for firstly, you're still doing your course project, right? I hope I can still provide some sparks or inspirations for your course project in terms of what you want to do. Although you may have submitted your course project proposal, I want you to know that you can still change the topic of your project. Okay, there is no limit on that. If you think that okay, I just found another interesting topic, um, I want to do it and I have the data for it, you can just tell your TA, and you can change the project. Of course, you may want also to consider if the new one is doable in the next 3 or 4 weeks. Okay, and also you also need to know that even you have finished your proposal. I mentioned this before, but I have to emphasize this again. Um, even you have selected a topic for your course project, make sure it's doable. Do not make it too big because you don't have time for that. And also, you should have already collected data for your topic because there is not so much time left. Okay. So the first lecture of remote sensing's application will be about urban remote sensing. Okay, so firstly, I want to review applications of remote sensing and ask the question that why we need remote sensing in urbanized areas. Okay, the importance or the necessity of urban remote sensing. And then I'm going to list some challenges in urban remote sensing currently. Okay, some of these challenges, there is no perfect solution to solve them. For example, scale issue, you can never solve that perfectly. Some of those challenges, I would expect that maybe in future there could be a perfect solution for one of them or for some of them, but not sure about that. Okay, I will just introduce all those challenges. Okay, and then I want to introduce land cover classification for urbanized areas. You may ask, why do I need to know this again? Because I learned that from a previous lecture. Okay, different classification methods, and I guarantee you I will give you some more new information on the land cover classification in urban areas with new methods. Okay, I introduced basic classification methods that can be applied universally, not only in urbanized areas, but also in rural areas, in wildlands. But trust me, urban area urban areas, they're very special in terms of classification. And by the end of, for the last part of this lecture, I want to introduce a little bit of what I did for my PhD dissertation, because it was about remote sensing's application in urbanized areas. Just a little bit. I do not want to make it very complex, or I do not want to scare anyone. I just want you to know that all the information I provide here, all the methods, issues, challenges, you could, I mean, you will probably encounter them in future if you are going to study or you are going to work in remote sensing discipline. Okay, let's get started. So firstly, some reviews for applications of remote sensing. So we know it can be applied for for identifying vegetation. Okay, for example, we can use vegetation index to identify vegetation, and we can also do biomass estimation. We can do phenology metrics. Okay, so we can address vegetation in real world, and we can do water remote sensing. Specifically, we can do ocean remote sensing, right? Ocean color, we can find issues or retrieve information from the color of ocean water, or we can do surface temperature and salinity measurement using remote sensing methods. Some of them optical, some of them microwave, but they're remote sensing, right? And hard targets and oil spill detection, for example, if a ship sunk, not completely, of course, in the ocean, we can find it. Okay, even a plane crashed in the ocean. If we can narrow down the area, we can use satellites to find that plane. They're called hard targets. Or an island, that it can also be considered as a hard target. Okay, if there is oil spill, there is other ecological disaster, we can use remote sensing to address that. Okay, agricultural remote sensing is very similar to vegetation remote sensing, right? Because when we're talking about agriculture, we're basically talking about crops, right? And they are plants, they are vegetation. So crop identification, pest and infestation, detection. How do I know if this specific crop is infested? We can identify that from the reflectance spectrum of that crop. Okay, healthy vegetation and unhealthy vegetation, they have different spectra, reflectance spectra. Soil moisture estimation, this is totally not vegetation remote sensing, right? Because we're talking about agriculture. The condition of soil is also crucial, right? We can use remote sensing to address that. We can also establish empirical models or rational models to predict the yield of different crops, right? And also we can use remote sensing to address the sky above us. Okay, not outer space, but atmosphere of the Earth for weather forecast, for atmospheric chemistry detection. Okay, different chemicals in atmosphere. Some of them, they can be detected by remote sensors. And we can also create radiative transfer theories, and they can be applied back on remote sensing to make it more accurate, or they can be applied in other disciplines to help people address other problems. So these four, say, categories of remote sensing applications, they are important, and I have explained why they are important and some very simple examples. So why urban remote sensing? Because urbanized areas, they are important. Cities, they are important, okay? So only 10% of Earth's surface is inhabited by human, okay? And 1% of that 10% of the Earth's surface is urbanized, okay? Which is 0.1% of Earth's surface, right? 1% of 10% of the whole Earth surface, that is 0.1%. But approximately half the planet's human population, of course, live in this 0.1% Earth surface, which is urbanized areas. So you should know that these are data, these are figures, right? They're reliable. So it's important because urbanized areas, they're very close to our daily life, okay? At the beginning of 20th century, only 13.3% Earth population lived in urbanized areas, okay? And that number doubled in 50 years, more than doubled. And then doubled again in the next, doubled again by the end of 2050. Of course, this is a projection, but you know that more and more people around the world, they are moving to cities because of why? Because it's more convenient, it's more comfortable, it's safer to live in cities, right? Right. So that's why it's important to address issues in urbanized areas. For example, the atmosphere above the urbanized areas. Okay, how does urbanization affect the air, the atmosphere? I mean, above the city, above a city. And for example, urban heat island. How does urbanization affect surface temperature and air temperature of urbanized areas or the areas surrounding cities? Okay, these problems, they are close to people's life. Specifically, they're crucial to people's health, to people's thought, to people's feeling. Okay, to the environment, right? To the environmental pollution. Okay, so we can also use remote sensing to address these problems. Of course, they have been addressed by traditional field measurements and field works, but since now we have remote sensing, remote sensing is not something that is very new, but new technologies have been developed continuously. And today, when we're talking about remote sensing, we can use traditional remote sensing methods. We can use new methods to address issues within urban areas. Okay, so that's why we want to use this tool, remote sensing, to address urban areas. Okay, so some example here about the explosion of big cities. So this is a GIF showing you the development of Beijing, which is a capital of China from 1985 to 2010. Okay, sorry, 15. So this is 1985, 1995, 2005, 2010, and 2015. Okay, you can look at this GIF while I'm talking here. So usually the dark areas in an image, they are they are wild lands. They are say they are bare soil. There could be forest, but anything non-artificial. Okay, they are dark, and bright areas in an image, if there is a city, those bright areas, they're usually urbanized areas. So in this image, you can say, for example, here, okay, to the top right of this image, we have a specific area that is very bright, and it is this area, this building, this facility here is expanding, right? Right. This is a capital airport of Beijing. You can say it's a bright area because we can say there is asphalt, concrete, right? Because it's airport. So you can say this city expanded a lot from 1985 to 2015 because in general, you can say this picture is getting brighter and brighter, and you can say there are more and more linear features, which means there are more and more rows, and there are more and more smaller squares, which means there are more and more city blocks and buildings, right? So if we compare the image from 1955 and 1985 to 2015, you can see the difference. Okay, the later image is much brighter than the first one, than the former one, because the city is enormous right now. And 6.2 million was the population of the city back in 1985. I know it's a big one for a US city, but that was the capital of China. And right now, not right now, 5 years ago in 2015, 21.7 million people, they live in this huge city. Okay, so this is the speed of urbanization, and it is not only happening in developing countries like China. It is also happening here. So it's a similar GF for Houston. Okay, okay. So 1985 to 2015, you can say it's even more clear that, I mean, the expansion of US city is more obvious because the surrounding rural area uh, uh, is very broad, is very vast. So now you can say that the image again is becoming brighter and brighter. You can say this city is expanding to the northwest, right? So this area, you can say more and more linear features can be found as the time goes by, right? So urbanization is happening everywhere around the world, okay? And people are moving, even though they don't want to. Sometimes the city will devour this, will eat up all the surrounding rural areas. And people used to live there. They used to be living in rural areas, but now they are living in a city, right? So this is urbanization, and we need to address associated problems, okay? So some challenges in urban remote sensing. So the first challenge here is spectral issues. Do we even know who is who in an urbanized area? I mean, which part of the urbanized area, of this specific urbanized area, is asphalt? Which part is concrete? Which part is vegetation? So who is who means which land cover type is which land cover type. So do we even know who is who, or do we even know which is which in terms of land cover? So here is a figure showing you very typical materials and land covers you can find in urbanized areas. For example, water, artificial turf, asphalt, centipede grass, concrete, red brick, sand, sandy clay soil, right? So you can see their spectra are very complex. And when we're talking about addressing urbanized areas using remote sensing, the first question is that, can we classify all these complex materials? Because in wildlands, there could be vegetation, there could be grass, there could be bare soil. That's all. Basically, that's all. There is no, say, concrete, asphalt, metal, glass, all these materials, bricks. There is no these materials in wildlands, so we don't have to worry about them. But this is city, okay? So classification in urbanized areas is very complex. And this is Landsat 7. And all these small rectangles, they are representing the wavelengths covered by all bands of ETM plus on Landsat 7. So you can say they are non-continuous, and which means some part of the spectrum is missed by this sensor, right? And some of these bands, they're very narrow. Even they are continuous, they're very narrow, okay? So from 400 nanometer to 2,500 nanometer, there are only 7 bands. So how to address this issue? There is a new technology, maybe it appeared in 20 years ago or no longer than 30 years ago. It's called hyperspectral remote sensing. I mentioned this concept before. It means that we want to use a very high performance sensor to cover the whole range we care about. For example, Hyperion is a hyperspectral sensor, and this yellow bar here represents 220 bands from this sensor, covering the same range from 400 to 2,500 nanometers. So compared to ETM plus, these 220 bands, they can accurately address all spectra of these materials continuously. So any detailed spectral feature of these materials can be captured by these 220 bands. So you say, okay, then issue solved. Spectral issue no more. No. Now we have 220 bands. So we have a huge amount of data. And that is still a problem. It's like we're swimming in the ocean of data, but we're thirsty. We cannot drink. We're surrounded by water. We're surrounded by data from 220 bands, but we cannot use them sometimes because it's just too large. So normal computers cannot deal with them because the hardware is not big enough, or the speed of the computer is not good enough. The CPU is not powerful enough. The GPU, your video card is not powerful enough to visualize this data. Okay, so the issue is still there. We now have hyperspectral sensors and hyperspectral data. Sometimes you have to pay for them. Of course, that is also issue. But that is the issue that is not very crucial, right? As long as you have financially supported by some institution or somebody. But still, even you have the data, we still have spectral issue because sometimes we cannot address them efficiently. Okay, this issue, I mean, has not been solved perfectly. Spectral issues, right? We have a hyperspectral sensor, but how to deal with the data, how to manipulate data is still the problem. People from electronic engineering, people from computer science, they're trying to develop new methods in terms of software and hardware to address huge amount of data today. There will be improvement, but you should know still that is a problem. Okay, and the second issue, second challenge I want to talk about here is about scale. So what is the correct? It's not proper to say correct. What is the most suitable? Say that because there is no wrong scale to research a city, to study a city. Let's just say what is the most suitable scale for addressing cities using remote sensing technology. So let's just check different typical scales for different applications, okay? So we have micro scale. For example, the spatial resolution of the image is 10 kilometer. So this is a example. This is a figure. You should expect one a pixel is 10 by 10 kilometers. Okay, so at this scale, we usually address climate change, atmospheric properties, and ocean currents. Obviously, this is not a very suitable scale for a city because a city is simply just too small at this scale. For example, this is Cleveland, right? So Columbus may be somewhere here. So if one pixel is 10 by 10 kilometers, maybe a dozen pixels is good enough to address a city like Columbus. That is obviously not good enough. From a dozen pixels, what can you retrieve? Okay, so that's micro scale. Then we have mesoscale or mid scale. For example, 1 kilometer by 1 kilometer spatial resolution. It's the resolution from MODIS. This scale is good for regional meteorology, okay? For land use, land cover detection, for example, LU, LC, that's the Euro reference data set for land cover in US, right? I mentioned previously. So this scale is pretty good for, also good for surface temperature analysis. Okay, we can use thermal bands to retrieve land surface temperature of the interested area. And again, for this scale, studying cities using remote sensing is not good enough. Again, okay, for example, this is Wisconsin. This is where I stayed for my PhD degree. And here is the city of Milwaukee. Actually, this area is the Milwaukee metropolitan area. You can see that in this image, it's just still too small. Okay. It's pretty hard to address very detailed to retrieve very detailed information from the city. And next level is proper for urban study. It's called microscale. So 30 meter by 30 meter. Usually this is a widely used spatial resolution, ETM plus TM, which means land, in general Landsat family sensors. They are using this spatial resolution. It's pretty good for urban area LSA, land use, land cover studies, because each pixel covers 30 meters by 30 meters. So each block, even a small block, can be addressed by several pixels. That's good enough for us. Okay, of course you can ask for more. Okay, I will talk about even higher resolution later, but in general, this is good enough, because you can say in this image, we're still looking at Milwaukee metropolitan area. So on the right side, we have Lake Michigan. This is the downtown Milwaukee, and the surrounding areas, they're right here. Okay. And all those residential areas, commercial areas, CBD roads, they can be clearly addressed by this spatial resolution. So it's good enough. Actually, this is the most commonly used scale for urban studies with remote sensing. So 30 meter micro scale. And it can also be used, this scale, image at scale, at this scale can also be used for something called subpixel analysis. This is a new method for urban classification I mentioned at the beginning of the lecture. So I introduced basic classification methods previously, and some of them they are object-based, right? But most of them, they were pixel-based, which means that we're going to give each pixel a specific class after the classification, right? Supervised, unsupervised, no matter. There must be a class for a specific pixel. But in urbanized areas, there are just too many materials and land covers. Okay, sometimes pixel level is not good enough. We need to divide a pixel into even smaller units. Okay, these units, they are not image units, because the smallest unit in an image is pixel. When we're talking about subpixel, we consider that we can divide a pixel into even smaller units, okay, and give each part of the pixel a specific class. Okay, that's called subpixel analysis, and it is needed from this scale, from 30 meter, because just imagine you're standing at a crossroad in a very busy city, okay, and you are the center of a pixel, and a 30 meter by 30 meter pixel is covering the area you are standing. So within this area, 30 meter by 30 meter, is it possible that there is only one land cover type? No, it's not possible. There must be, I mean, in most cases, okay, I'm not going to say absolutely. In most scenarios, in a very busy city, when you're standing at a crossroad, there must be concrete or asphalt for road. There must be grass. There must be trees, right? If there is a building, there must be roof, and roof can be something different from concrete and what? And asphalt. It could be some materials that is waterproof. There could be metal, there could be glass. So within this 30 meter by 30 meter pixel, the land cover composition could be very complex. That's why pixel level analysis is not good enough. Okay, we want to differentiate vegetation, concrete, asphalt, metal, glass from each other within this pixel, within this very small 30 meter by 30 meter pixel. You say, why don't you use this method? Why don't you care about this different materials? One you are doing study at this level or even larger level, because it doesn't matter if a pixel covers 10 kilometer by 10 kilometer, you are looking at this whole continent directly. Why do you even care what is going on within a 10 kilometer by 10 kilometer area? Okay, we consider each pixel at this level pure, which means there is only one land cover type. Okay, vegetation, water body, bare soil, or whatever. It's not necessary to do sub-pixel level analysis. Similarly, we don't have to do this at mesoscale. But when we're talking about city, it's very complex in terms of land cover types. We're not looking at rural areas. Rural areas, they're easier to classify. Now we need sub-pixel analysis. And like I said, if the spatial resolution increases continuously. So this is Miller Park, the baseball team, home of the baseball team from Milwaukee. Okay, so this is an image with a spatial resolution, I think 0.6 or 0.4 meter, which means 40 or 60 centimeter. Okay, so Icona's QuickBird, they can do this level remote sensing. Okay, usually at this level we do population estimation because we can count the number of houses within a residential area, and we estimate the average population in each house. We multiply that by the number of houses, then we have a population estimation, right? We can also do urban 3D modeling, okay, using LiDAR data. LiDAR data can provide very accurate elevation measurements, okay? And the spatial resolution of a LiDAR sensor can also be very high. So actually, if you are using a LiDAR sensor to scan this baseball card here, you can have the 3D model of this huge building because you know the elevation of each point of this building, okay, as that point can be detected by the LiDAR sensor. Okay, we can also do high accuracy LULC change detection. But at this level, sub-pixel analysis is actually not necessary. Why? This is a very interesting question. Because when the spatial resolution is as high as 40 centimeter, each pixel should be pure, right? So you can simply use your hand to draw a 40 centimeter by 40 centimeter square on your desk. Imagine that you draw that same small square on the ground of a city. Within that small square, it's most likely that there is only one land cover type. So that pixel is most likely, most pixels in this image, they are pure pixels in terms of land covers, because within each pixel, it's most likely that there is only one land cover type, because each pixel is just representing a too small area in the real world, 40 centimeter by 40 centimeter. Okay, so sub-pixel analysis is useful at this level, 30 meter by 30 meter. And it's more useful in urbanized areas than in rural areas, because in rural areas, the land cover composition is just too simple. And in cities, it's not simple anymore. We have different materials and land cover types. Okay, so this is a scale issue. You can say that you need to choose a scale before doing any remote sensing project or research, right? So if you care about the city, you need to choose micro scale. If you care about the climate change of a continent, micro scale, right? If you care about the details, very accurate details of a specific area, then maybe use some commercial satellites to capture some images at very high spatial resolution. Okay, smaller than 1 meter. And in most scenarios, you have to pay for them. Okay, Iconos, QuickBird, they are not cheap anymore. I mean, not anymore at all. They have never been cheap. You have to buy those imagery. Okay, so the next problem is called MAUP. But I will just stop here for this video, and I will continue to introduce the challenges and other content of this lecture in next video. Okay, thank you.